Okay, so we're going to look at explaining the interference pattern. We have talked about this a little bit, and we did say that when the path difference between two waves is zero wavelengths or one full wavelength or two full wavelengths, then they overlap and that means they are in phase, so they produce maxima. And when that path difference is half a wavelength, you end up with a trough meeting a peak, and they are out of phase and they cause destructive interference and cause a minima. So now we're just going to write this down officially now. So the answer to explaining an interference pattern lies in the idea of path difference. We need to compare the two different paths taken by the waves from the two sources to the point in question. So in this diagram, we've got S1 and S2. They could be two dippers in a ripple tank going at the same frequency, two loudspeakers connected to the same signal generator, or two slits in a metal sheet with microwaves, so microwaves passing through the same microwaves passing through but two slits. Okay, so we've got S1 and S2. They are coherent, they're coming from the same source. Okay, so at point P there, that's right in the center. You can see that center line there, and point P is slap bang in the middle of S1 and S2. So those paths are traveling the same distance to get to point P. So point P is a point at the center line of the pattern at which constructive interference occurs. P is the same distance from S1 as it is from S2. So the distance S2 to P minus S1 to P, because they're the same, it's just 1 minus 1 or 2 minus 2, it's 0. So the waves arrive at P in phase. Because they're in phase, that means constructive interference occurs, and waves of a large or positive amplitude occur here. So that'd be the biggest because less energy would be lost as well. So they're traveling the exact same distance. They will arrive with a crest meeting a crest, trough meeting a trough. No difference at all in the wave paths. So they're in phase, and the constructive interference occurs, and you get a maxima. And this result will be true on any point on the dotted line. I don't think it's dotted in this, so this is basically this bit here. Let's say green line, which passes midway between the sources, provided the two sources are in phase, because they both travel the same distance. If the two sources were exactly out of phase, the center line would be one of destructive interference. So if one was half a wavelength out when it started off. However, in a ripple tank, the water would only be a flat calm if the two sources were producing waves of exactly the same amplitude. Right, you don't really need to worry about that too much. The middle point is always going to be a maximum at higher level. So now, right, we're going to consider another point also with constructive interference. So here we've got S1 and S2 again, they're the same, coming from the same source, so they are coherent. And we've got our maximum here. That's our very center maximum, where they're not traveling any differently. They're traveling the same distance. Then we have destructive interference at this point. So that's 0 wavelength difference. That must mean one has traveled half a wavelength more than the other. A crest would meet a trough, and we'd have destructive interference. Then it would go back up, so it should be half a wavelength. Then it would go back up to constructive interference. So that is one full wavelength difference. So we'd have a crest meeting a crest again. They'd be in phase, and you'd have constructive interference. And it would keep going along. So the next one would be 1.5 wavelengths different. Then it would be 2 wavelengths difference. And the same happens down the way as well. So for destructive interference, that would be a half a wavelength difference. It'd just be S1 to P would be traveling further than S2 to P, and that would be one full wavelength difference. So P2, which is this one here we're looking at, we've got constructive interference. So P2 is a larger distance from S1 than it is from S2 by sorry, that's the wrong way around. It's a larger distance from S2 than it is by S1 because this distance here is larger than this distance. Doesn't really matter too much. But we just need to know that one is larger than the other. And it is by exactly 1 wavelength, because it's the first maxima that we see or hear after the 0, 1. So the distance S2P minus S1P, P2, sorry, is going to be 1 wavelength. So that's 1 wavelength. So the path difference is 1 wavelength. Because the path difference is 1 wavelength, the waves arrive in phase. And because they're in phase, that means a trough and a trough and a crest and a crest. Constructive constructive interference occurs. There we go. And again, waves of a large or a positive amplitude occur here. Okay, so we've got another maximum when the path difference is one wavelength. A similar effect occurs at P2 dash, which is this one here, in the lower half of the pattern. In fact, for the points P4, P6, etc., the result is the same, but the path difference at P4, which would be the next maxima, would be 2 wavelengths, and P6 would be 3 wavelengths. So it's each one's adding a wavelength. So that would be P3, and that would be P4, and then you'd have a minimum at P5, etc., etc. So we can generalize for all regions of constructive interference, the path difference has to be a full number of wavelengths, so n wavelengths where n is 0, 1, 2, 3. So if the path difference is 0 or 1 wavelength or 2 wavelengths or 3 wavelengths or 4 wavelengths, then you'll always get a maxima. So it's all about that path difference. If you take one path from the other and it's a multiple of a full wavelength, you'd have a maxima. So what about the minima? Okay, so now we're looking at P1 dash. Okay, so P1 dash, so this is our 0. Okay, that's a maximum. And then P1 dash would be a minimum, and then we'd have P2, which would be a maximum again, P2 dash, just because it's dash because it's down the way rather than up the way. And you'd have the same thing going up the way. You'd have P1 would be a minimum, P2 maximum. But in this case, we've got a path difference of half a wavelength, so we're going to have a minimum. So P1 dash is a smaller distance from S2 than it is from S1, but only by half of a wavelength. So the path difference between them is a half a wavelength. So waves, because it's half a wavelength path difference, then you'd have a crest meeting a trough. So waves would arrive exactly out of phase. So because of that, destructive interference occurs, and the crest cancels out the trough basically, and waves of 0 amplitude occur here. So you'd have a nothingness. So a similar effect occurs in the upper half of the pattern. In fact, for points P3, P5, etc., the result is the same, but the path difference at P3 would be 1.5 wavelengths. Let me do that. Try that one again. Make it a little bit clearer. 1.5. And P5 would be 2.5 wavelengths. So a multiple of 1 plus a half wavelengths. So we can generalize for all regions of destructive interference, so where they cancel each other out, your path difference would be n plus a half wavelength, where n is 0, 1, 2, 3. So 0 plus a half is a half, 1 plus a half is 1.5, 2 plus a half is 2.5. So if it's any sort of multiple of a half wavelength, then you end up with a minima, a destructive piece of interference. Okay, so we're going to do an example of this. So I've written the first one out already because otherwise it would take me forever to write it with this pen. So for example, 2 identical loudspeakers, X and Y, are set up in a room which has been designed to eliminate the reflection of sound. So that's just a case of like, what would you do if you wanted to keep this for a test kind of thing. The loudspeakers are connected to the same signal generator, so that means they're coherent. Okay. So we've got there, shows us from X it's a 4 meter distance and from Y it's 5.2 meters distance. Part A. When a sound level meter is moved from P to T, maxima and minima of sound are detected. Explain in terms of waves why the maxima and minima are produced. So I've written there. So when path difference is a multiple of a full wavelength, the waves are in phase and constructive interference occurs. So you'd see a maximum. And when the path difference is 1.5 wavelengths, or sorry, half a wavelength, or 1.5 wavelengths, or n plus a half wavelength, the waves are out of phase, so you'd find destructive interference. So each time, so basically that's what you need to write. So you need to write about difference in path difference. Are they in phase or out of phase? Or is it constructive or destructive interference? As you move that the sound level meter, the path difference will change as you move it along. So it will go from 1 full wavelength, so or 0, 1, 0, half, 1, 1.5, 2. Okay. Part 2, part 2. The sound level meter detects a maximum at P. So this is our maximum. As the sound level meter is moved from P, it detects a minimum, then a maximum, then another minimum when it reaches Q. So min, max, and then another min there. So it just helps us sort of write down what you're seeing, because I think it helps me to visualize it. So we've got max, min, max, and min at Q. Calculate the wavelength of the sound used. Okay, so we know P is our first maximum. It's the sort of middle maximum. So that's our 0 path difference point. Okay, so the path difference at P would be 0 wavelengths. Okay, then our first minimum, we know would be a half wavelength. Then our next maximum, we know that would be 1 wavelength difference. And then the next minimum, which is the Q, which we want to find out, is 1.5 wavelengths difference. Okay, so that's just what we found out because we know what's been detected. So we know it's been a minimum, maximum, then another minimum. So we need to calculate the wavelength of the sound used. So at Q, path difference is 1.5 wavelengths. Okay, we also are told the physical path difference. So path difference path difference is going to be, so we've got one of the paths is 4 and one is 5.2. So 5.2 minus 4, which obviously is 1.2 meters. So we know the path difference is 1.5 wavelengths. We also know the path difference is 1.2. So 1.2 is 1.5 wavelengths. So 1 wavelength would be 1.2 divided by 1.5, which comes to 0.8 meters. Okay. Part B. The sound level meter is now fixed at Q. The frequency of the output from the signal generator is increased steadily from 200 Hz to 1000 Hz. So part BI asks, what happens to the wavelength of the sound as the frequency of the output is increased? So BI, well, if the frequency increases and the speed is the same, so V equals F lambda. So frequency is speed divided by wavelength. So if speed stays the same, then if frequency increases, the wavelength decreases. So wavelength decreases. And part 2, as the wavelength is changing, part 2, explain why the sound level meter detects a series of maxima and minima as the frequency of the output is increased. So we know because the frequency is changing, the wavelength is changing. Okay, so the path difference will be changing from full wavelengths to half wavelengths as it goes along. Because the wavelength is changing, the path difference constantly changes as well. So what once was a wavelength difference will no longer be a wavelength difference because the wavelength has changed. So that will constantly change as well.